Welcome, developers. I hope you like my new background. I'm experimenting a bit and we'll see how it works out. In the second installment of Programming with SimConnect, we're going to start with the messaging bits. This time we'll start looking at how we receive messages from the simulator and go through the different ways to detect there are messages waiting for us. Next, we'll look at requesting the simulator to send us its system state. This will give us some basic information on what it is doing. And we'll finish with asking it to tell us as soon as the system state changes. And here we have a lot more choice in different state information that we can ask for it. So let's go. The most important bit to understand is that for Microsoft Flight Simulator, and the other flight simulators of course, is that its first priority is doing its own thing. Simulate the world and the aircraft in it, and provide as well as possible the stunning graphics we're expecting from it. But given that priority, we present it with a problem because we want it to send us data on what is happening, and we want to tell it to do things, and we want it pronto. So it kind of needs to keep us at a respectful distance. It will look at our requests when it has time, and it will answer when it feels like it. This means that we send our requests, but accept that we shouldn't wait for a prompt response. In programming, we call this asynchronous communication. The simulator is a separate process in Windows, and this means we cannot access it directly. SimConnect provides us communication through a so-called pipe, through which messages are sent and received. This pipe can be created looking like a file, but it can also be made available on the network using IP version 4 or IP version 6. So yes, you can connect to the simulator through the network from another computer. Of course, Windows Firewall has to allow the opening up of this port, and the other computer must also be running Windows because you need the SimConnect library on that other computer. Default is local access through a file system pipe. So, given that we don't know when a message is coming, how do we ask SimConnect for that next message? There are basically two calls we can use. One of them is called SimConnect_getNextDispatch, and the other one is SimConnect_callDispatch. The difference is getNextDispatch asks SimConnect to give us the next message if it is available. If that call succeeds, you will get a pointer plus an indication of the length of the message, and then you can process that message. With callDispatch, you are giving SimConnect a function pointer, and SimConnect will call that function to hand it the message if there is one. Whichever one you use, you should keep calling this until it fails to make sure that you have processed all messages that are currently queued for processing. Then you wait a bit or do something useful instead before you try again. Then, when we do get a message from SimConnect, we need to find out what kind of message it is, find out what message we sent earlier that this could be related to, and then take an appropriate action based on that. All SimConnect messages follow the same pattern. They start with first an unsigned 32-bit integer telling us how long the message is. This means that no matter what type of message we get, we always know beyond the pointer that we get past how far we have a valid piece of memory for that message. Next, we get an unsigned 32-bit integer with the version number of the SimConnect server. This is hardly ever used, but it can help us so that we know actually how old the simulator is that we're talking to. The third item is again an unsigned 32-bit integer with a message ID, and this tells us exactly what kind of message it is. After that, there follows the rest of the message. How much that is and how that is structured is dependent on that message ID. These first 12 bytes of three 32-bit integers we can now subtract from the length of the message, and then we know the length of the remainder. There is an enumeration called SimConnect RECV ID that tells us all the different values of a message ID. The first four are special. Message number 0 actually is very special because you hardly ever get a message from that. It's a no-op message, simply saying there is no message. The second one, type 1, is one that you hope to get as little as possible or never if possible, because it is a so-called exception message. It means that SimConnect has some kind of error to pass on to us from the simulator. It will probably mean that we asked for something that it couldn't do, or we asked something that it thought nonsensical. The third message type, type 2, announces the identity of the simulator. We get it when the connection is first established. It will give you name and version of the simulator, name and version of the SimConnect library, and some other information. The fourth, type 3, announces that the simulator is shutting down. This can be used so we can close the connection to the simulator because we know the connection will be invalid anyway. We can then use that to either shut down ourselves or just simply update a state information in our application that tells us that we need to re-establish the connection as soon as possible. So let's start with the simplest and perhaps you could call it the dumbest approach. So envision that you're making a long trip in the car, and in the back of the car is a restless and impatient person interested in only one thing. Are we there yet? In computer science, we call this effect polling. You check if a message has arrived. If so, you process it. If not, then depending on how impatient you are, you either wait a bit or then you immediately go back to step 1 and ask, is there a message already? There are two things you have to be careful with. The wait a bit could be counted in milliseconds or more, but if you don't do that and immediately check again, you might run into a modern virus or malware protection tool that you have on your PC that is saying, hey, there is this application and it's doing kind of a denial of service attack on another application, and that doesn't sound good. I've noticed that if I just use polling without any pauses, my virus checker at least immediately marks my test application as a piece of malware and blocks it. So let's see how this polling approach works in code. Okay, here we are in our first SimConnect app as it was made in the first lesson. So let's add the scanning for the messages. And we'll call that handling messages just to explain why you will find the name handle or handling a lot. And we'll start with just a simple method here or function. And this will scan for messages and then do something with them. So we need a pointer to messages. This is going to be given to us by SimConnect. And of course, we're going to receive the length of that message. And lastly, we'll need our H result. So we're going to loop. And we're going to loop as long as we get messages. We'll use getNextDispatch, which will give us the message itself. So it needs the handle. It needs an address to our pointer for the message. And it needs an address for the variable that will contain the length of the message. And we're going to take a look at what's in that message. So depending on the type of message, so let's start with the first message that we can actually do something with. Which is the open message. If we receive that, we're going to create a new pointer which points to the new message. And we can now print out some messages. I'll just copy those. Let's see, we don't need that. Oh no, we do need that, sorry. And we'll do a little bit of formatting here. So you can see what we're getting out of this message is the name of the simulator, that is here, the first field, and then the version of the simulator, the major number and the minor number, and then the build major number and minor number. And we're printing them out in a nice format. Same for the SimConnect version. Again, first a version, major, minor, and then a build, major, minor. Okay. So, the next message that we want to look at is the quit or close message, because that is telling us that the simulator is shutting down. Now we can, of course, pick up more messages, but we'll just put in the default for the moment, printing out that there was some message that we don't have a handler for. Okay. Add a break. That's done. Okay. Now, when we've processed all messages, of course, we shouldn't stop handling them. And we'll put that around this. So we're going to use a Boolean connected. We'll put that at the top. And we'll set it to false when we receive message that the simulator is shutting down. Okay. So now what we need to do here is set our connected to true, and then handle messages. Then when we're done handling messages, that means that the simulator is shutting down and we can do a close. Of course, there is something still missing here. That was the one thing I warned about. And that is the small wait that we need to do between successive sets of polling, because otherwise we're going to be marked as malware. So we'll add here a call to sleep for just 100 milliseconds. And this is something we only need to do if we're still connected. Let me format that. Like this. And that should work. See, build succeeded. Now initially, when we run it, it will immediately stop, because of course the simulator is not running at the moment. And let's start that.
A few moments later.
Okay, I've started up the simulator. So let's run our program. And here you see, welcome to this first SimConnect app, successfully connected to MSFS. And then it receives the open message and prints out the information. Okay, I'm now going to stop the simulator. And you see simulator is shutting down, and then we disconnected and the program ended. Okay, that was a relatively simple example, but you'll see that that switch statement when we actually get the message and then want to check what kind of message it is, can become quite large and ugly. We now can also use call dispatch instead of get dispatch, but still we need that switch inside there. So callbacks are very useful when cleaning up your code. So take a sorting function, you write a sorting algorithm once, but you don't include any information on how to sort. So am I sorting alphabetically? Am I sorting numerically? Am I sorting low to high or high to low? Is it actually an array of records or structs and I want a multi-level sorting? All that kind of stuff you can now put into a parameter function. So you write the sorting once, and how you sort it is up to the caller. In modern C++, apart from just regular functions, we can also use lambdas. I like lambdas a lot. A lambda lets you create a function as a value. You can even let the lambda refer to a local variable or a parameter of the function where you are defining that lambda. So it's very powerful. What we now can do is create an array with separate callbacks for each of the message IDs. We'll also allow for a default message handler, so we don't have to register one, and we have a default one, for example, one that simply says, I don't know how to deal with a message with message ID and then the number, but the ones that do have a handler, you can then call. The handler class wants a function that receives a pointer to a message and a length. For specific messages, it will then cast the pointer to the correct type for me. This is all done using templates. The result is nice and clean, and let's take a look at what that looks like. So let's start with the program we had from part 1, which did the open and then the close, just like before. We're still using a simple connection, but now we're going to add a message handler. And that is available if we include the correct header file, of course. And we have here a polling handler. So this handler, of course, needs to know the handle for the connection, so we give it the connection object. And this handler also knows about the quit message in the sense that it can close the connection for us as soon as it sees a quit message coming in. So we set its auto-closing feature to true. Now, the next thing we need to do is to add in the handlers. And let's start with a default handler that will pick up any message that we haven't given any specific handler for. Sorry, set default handler. And here we're going to add a lambda. And it's going to get that same pointer we saw in the previous one. So it's the SimConnect receive pointer for the message and a D word for the length. And all we're going to do with it is just print out a complaint that we don't have a handler for this. we'll use it, do it just like in the previous one. So we'll use format to make it a nicely formatted message that tells us the type of the message and the length of the message that we just ignored. And of course, we do need to make sure that format is included. Like this. Okay. So we now have a default handler, and the default handler is going to take care of anything that we don't have a specific handler for. So the next thing we want to do is give it a handler for the open and for the close message or quit message. We're going to register a handler, and we want this handler to be for a specific message type. With this ID. And we're going to give it a function that we still need to make. So handle open will do that. And because we are using a templated method, this handle open will be able to receive this message type here without needing to cast it. We'll first also register the quit handler. Like that. And let's write those two. Now, I already said we're going to get a casted pointer for us, but we're going to get it as a reference. So we can say const SimConnect RECV open reference message. Oh. And just to save us a bit of time, I'm going to copy that from another editor. And I'm using here a small function called version to create a nicely formatted version string. So I'll copy that as well. You see that it returns a string. And because it's inline, this will be optimized away. So it will be pretty nice and quick. So let's add handle quit. Same way. And we're just going to print that the simulator is shutting down. Of course, this means that we're not using the message, so we'll add a maybe unused. Let's see. Did I make a typing mistake? Handle quit. No. Oh, just needed some time. Okay. So, everything is here. So let's start and use that. We'll put in a loop here. And while the connection is open, we're going to handle messages. And you see here that we are handling them by default for 0 milliseconds. Instead, let's put in something like 10 seconds. And we can do that like this if we add the namespace for chronoliterals. So, and that's all we need to put in here. So it will, for a time of 10 seconds, try to handle messages. If after 10 seconds there is nothing more available, it will come back. It will check if the connection is still open. That means the simulator is still running. And then go and try for another 10 seconds. If the simulator connection is closed, it will call close, which is still a leftover from the previous one, which is not necessary because we put it on auto closing. And then we can just print out that we're disconnected and stop. Okay. And now we can run this. And you see, of course, the flight simulator is again stopped. So let's start the simulator.
A few moments later.
Okay. I have started the simulator. And as you see, I also added a small message here about handling messages for 10 seconds. So let's start the program again. And you see we received the open message. And if we wait for 10 seconds, you will see it comes up again. So it just keeps repeating that loop. And if we quit, you see the program shuts down. Okay, This was just a simple example using polling. But there are other ways that we can find out there are new messages, which has advantages. First of all, Windows, and especially applications using the Win32 API, can improve on the polling approach by using the message queue that every graphical element on screen has. If your application has Win32 managed windows, each window gets that message queue and the operating system will put messages on there. It uses this, for example, to tell about user actions, things like button clicked or message closed or even application closed. These messages, of course, have message IDs just like our SimConnect message IDs. Of course, as an application writer, we can also add our own messages. In Windows, there is a special constant defined called WM_user that gives you a value that is the lowest available value for your user-dependent or your own custom messages. You can choose one of those and use it for SimConnect. You maybe remember that when we called SimConnect open in the first installment, we could pass it a window handle and a message ID. If we do that, SimConnect will now put messages on that Windows message queue to tell us there are new messages. This means that we can then wait or do other things until we get such a message. Let's take a quick look at how that works. Okay, so for a program that tests using the window handle, I actually just generated a very simple old school dialogue-based program. And here you see our win main. It's a different style. We don't have a simple main, but now it's a win main. And if I go down, then here you see the dialog prog, which is the handler of the messages in the message queue. And it's here picking up the button presses. And here we have our WM user SimConnect. This is the message that we're telling SimConnect to use when it finds new messages. And this is then for us the prompt to put in that while loop where we get all new messages. For the rest, it works the same way. The only difference is now, because we have a Windows application, we're actually going to put the text into a window. Take a look. The sources are all on GitHub. Take a look. Let's just see how it runs. And I'll put that in view here. So I have a very simple old school Windows dialog here. And we have a button, let's say connect. And you see that it immediately picked up the message from the simulator about its version and put it in there. And I can also do a disconnect. Great. So this is one way you can pull for messages or wait for messages by using the Windows messaging. Okay, so for the C++ version, of course, I couldn't resist. And instead of using the same application as a base, I this time generated the Microsoft Foundation classes version of that small UI application. It is a lot easier to program in if you want to use C++ and want to use the, at that time, starting to appear ideas about UIs being object-oriented. And you can see it's because it generates classes with objects in their fields in there for the different buttons and the different fields. And you can see here that I've added the Windows messaging connection and the simple handler. But you can also see that I haven't actually constructed them, and that's because they are generated separately, so that part is somewhere else. For the rest, we have here some additional methods for what to do when the connect button is clicked and when the disconnect button is clicked. And there is here a macro for declaring the message map. So if we go to the source file that goes with this, here you can see the constructors where the connection and the handler are actually constructed, and we register handler procs. There are two different ones because you have to use the one with the window parent pointer, while C++ requires you to also provide a default constructor, even though it's effectively not going to be used. But beyond that, if we go further down, if we have here the button connect clicked, and you see that here I do the open and pass it the window handle and WM SimConnect, which is something we made ourselves, defined ourselves, and that is the message that SimConnect is going to use. So on a message, the list you see here, WM SimConnect, and at that moment it calls the onSimConnect message method. So if we go down on SimConnect message and we dispatch all available messages at that moment. So it's pretty straightforward, and if we run the application, let me pull that into the screen, it looks exactly the same, apart from the fact that we now have an icon here, but for the rest, it just works just like before. You wouldn't use this normally unless you're a great fan of Windows 95 styled UIs, but it's definitely a big improvement on the C1. If you want to stay independent of this Windows messaging queue, you can also use a so-called condition variable. A condition variable allows you to tell the runtime or the operating system that I'm now going to do something else, or maybe even just sleep the entire process and wake me up when something happens. In Win32, these are called events. This is a bit confusing because an event is normally the message telling you that there is something, but yeah, we can't change that. So we're going to ask Windows for such an event and then tell it to pause until SimConnect puts a notification on that event. We have to pass, of course, the handle for that event to SimConnect when we do the open. Of course, we also have classes for this in C++. So let's see how that works. For using a Windows event or condition variable, we're going back to our first smaller program. And here you see the test connect. We're doing the call to SimConnect open with null pointer null, null pointer null or 0. Let's change that. We now need to call Windows and ask it to create an event. Because it's Windows, this will result in a handle. And we're going to call the create event system call. Now, if you want to take a look at what the meaning of all those parameters are, I invite you to go over to the documentation that Microsoft has put online for the Win32 API. I'm not going to do anything here. Sorry, this of course needs to go here. We do need to check whether or not we have received this handle. So if this handle is null, then for some reason or other, it failed to create. Oop. And test connects is what we return. So let's return a 1, a non-zero value. Okay, if we're here, then we succeeded. And all we need to do is now pass this event to SimConnect. Okay, handle messages can now work in a different style, but of course it needs to use that event handle. So we'll pass the event handle to handle messages. So again, we're running here a while, and instead of just checking whether we're currently connected or not, we're also going to ask Windows to block us until there is a message available, which is signaled using that event. So while connected, and wait for single object. We're going to give it the event handle. And we're going to tell it that we don't really care how long it takes, just wait. We're not going to do anything until there is a message. What we get returned is potentially, because as you see here, we're waiting for a single object. You can also wait for multiple objects. So we need to tell it that we expect that we finished waiting on the first, so object 0. And if so, then we have been notified that there is a message, and this means we can now have the inner loop, which will just simply pull out all messages that are currently waiting. So that doesn't change. So this stays the same. And if we get a ID quit, then we get a connected is false, which will then also break the outer loop. And this is all we need to put in here. Let's see if we made any mistakes. Nope. So we can now run, and of course we need to start the simulator. Okay, simulator has finished starting. Let's run again. And you see it works perfectly. You see also that it is now waiting. And if I quit the simulator, it wakes up and picks up the new message saying that the simulator is shutting down. Now you understand that this is a very nice way of doing it. It's a very efficient way of doing it, and using condition variables is usually the preferred solution. So this is what we're going to use from now on. Let's just switch to the C++ version next. So actually the C++ version of this program using a Windows event or condition variable is very simple to make from the polling version. We just need to use a different connection and a different handler. So let's first start by updating this. And here you see the Windows event connection. And the Windows event handler. So we go down to main. And put those two in here. And that is all we need to change. And it behaves just like before. Let's start the simulator again. Okay, simulator has started. Let's run. And you see it works just as before. And we'll just check if the quit also works. It should work. And you also see the handling messages for 10 seconds message. It's still there. We'll quit the simulator, and for the demos, this will be the last time that I'm going to start and quit the simulator this often, but just to show it. There we go. Okay, that was the last example with just connecting and disconnecting. Now let's move on to some actual message handling and go to the first real request. We're going to ask the simulator for its current state. There's just a few states that we can request in this way, and that is what aircraft is currently being used, what the flight plan is, or even the complete state of the aircraft if initialized, the so-called saved flights. These are returned as a path to a file. Next, you can ask the simulator if it's running or stopped, or if it's in dialog mode or not. Now, actually, that dialog mode is something that was present in the previous versions of Flight Simulator, and then I mean as in Flight Simulator X and before, or in Lockheed Martin Prepared, because if you are flying and then press escape, what would happen is that it would not just pause the simulation, but also black out the screen and put a dialogue in front of us. Microsoft Flight Simulator 2020 and 2024 don't use that, but the call is still there. Now, when we send requests to the Flight Simulator, we can assign so-called request IDs to such requests. This request ID is then used by SimConnect and the Flight Simulator when it gives responses. That way we can match up the response with our original question. This is done because we don't know when that answer will arrive. It will hopefully be quickly, but it might take a while. And we might send requests that give us a bunch of replies, or we might even send off a bunch of requests before we start polling for, or otherwise checking for, responses. In that case, we will get our answers in an order that we might not expect. And in this case, it's better to have that request ID. The traditional C-style approach is to use #define or an enum in your program and use constants that are defined top level throughout the application. Let's take a look at how that works. Okay, we're going to start with our example where we were with using Windows event instead of polling, and we're now going to add our first request. So we need request IDs. Let me clean this up a little bit. We're no longer interested in the receive ID open handling. We can leave that. So we'll add here the top an enumeration for the different request IDs we're going to use. As I said, we need to define that request ID ourselves, so it doesn't really matter what values we use. We're going to give it the name request IDs, and we're going to tell the compiler that we want it to be based on the SimConnect data request ID. So we know for sure that it is using the right type. And we'll just put in a few requests. Let's ask for the aircraft loaded. Let's ask for the flight file that's loaded. Also going to ask for the flight plan. Then we want to know if the dialog mode is active, even though that is no longer a thing with Microsoft Flight Simulator 2020 and 2024. And we're going to ask whether the simulator itself is running. And just to have something in here that's going to be of use later on, we're also going to ask it for a simulator state that actually doesn't exist. And we're going to ask it what simulator was loaded. Okay, we want to have a small function for this. We're going to call it RequestSystemState. And we'll pass it the request ID it needs to use. And the actual name of the system state that we want. Of course, going to test whether or not this succeeded. And we're going to request the SystemState. First, it needs the handle. Then it needs the request ID. And last, it wants the name. If this succeeded, we'll print out a small message. Like this. Of course, if this fails, we also want some kind of message. Okay. So now before we're going to handle that, let's first do the actual requests. Let's go here. If we succeeded in opening the connection, we're going to fire off these requests. So the first one is aircraft loaded. With the same name. And let's just copy this. Next one is not aircraft loaded, but flight loaded. Then a flight plan. Next, we want the, from here to there, the simulator or the dialog mode. Then we want the simulator state. Which just happens to be called just sim. And last, our non-existent sim loaded. Oh. Like that. Okay, so after sending off these requests, we just go on and continue handling messages. So now we need to actually handle these messages. This means we go back here and now add another case to our switch statement. And you will see that there is a message type for system state. And we're not testing for the type, we're testing for the ID, of course. So just like before, we'll cast the message. SystemState pointer. And cast our key data to that. And then we can handle the different system states. So we now need a second switch statement in here. Because we're not getting in this message the actual system state name back, we're getting the ID of the request back. So we'll start with the first. Aircraft loaded. And if it's aircraft loaded, then we'll print out the name of the aircraft file. Like this. And what we need to print out is the, as said, string field. Okay. Copy and paste this for the 6 messages that we send out. Second one was flight loaded. And that was also a string. Then we have flight plan loaded. The next one was dialog mode. And dialog mode is actually, although it's a number, it's a Boolean, so it's 0 or 1, and we'll print out on or off. So let's do that like this. And we now want the integer value. If it's unequal to 0, then dialog mode is on, and otherwise dialog mode is off. The next one is the simulator state. And we'll do it in the same way. And if it's true, then print running. And otherwise stopped. Last one is the sim loaded. And we'll print out a string. Okay. We do need to add a default in here. Even though we know it won't be there, it's better to tell the compiler that we are aware that there can be more values than just the ones that we are using. And we'll just do nothing. Okay. If we received any other type of message, we'll print out a message. So that's all in there, and that means that we can now run our application. Let's see. Did we make any mistakes? Nope. Okay, that's better. So, aircraft loaded. Then it got a message of type 1. Dialog mode off. Simulator state is running. And we do have some messages that we are expecting still. We got 2 type 1 messages. Those are the exception messages telling us about a problem that we'll take a look at next. Let's see if we made any typing mistakes. Dialog mode should be correct. Sim is correct. Okay, how about flight plan? Yes, flight plan loaded should be just flight plan. My mistake. Run it again. There we go. And you see now that it does receive a flight plan loaded message. However, there is no content because there is currently no flight plan loaded. I consider this a bug. I did make a report to Asobo about this, but they are still working on this area in 2024. Okay, that's the end for this C version of request system state. Now in C++, we're going to use a so-called handler class, a request handler. We're going to use layered callbacks. The first layer we've already seen, which is just the one for a message ID. In this case, for system states, that means we're going to tell our request handler that it needs to respond to any messages coming in of the system state type. Then we'll use that request handler to look into the message, determine the request ID, and then match up a handler we passed it when we asked it to do a request with the handler for that particular request. System state requests are one time only, so we're going to apply kind of a burner phone approach. We're going to get a collection of request handlers, and as soon as a message comes in that matches with a request ID that we have a handler for, we let that handler process the message and then remove the entry from our collection. There's a Boolean that we're going to use for this, and if that Boolean value is true, that's our signal that this is a one-time only reply, and we can remove the message when we're done. This will help us later when we have requests with multiple replies. If we get a message for a request we don't know about, we'll actually just pass the buck to the top-level handler and ask it for the default behavior of a message of that ID type. So let's see how that works. Okay, let's add the request handling here to our C++ application. We're not going to change anything here at the top. We're still going to use a default handler, just prints out a message that we're ignoring a message. We have our open and quit handlers. Those are all fine. It's just that now, if we open the connection and successfully, and we're now going to do something more. First thing we need to do is to set up that request handler. So we need to go up here and go for requests, request handler. Then we go down, and now we can add our request handler. We have it. And let's just call it request handler. And now we need to enable it on the top level handler. So we use enable, we give it the top level handler, and we give it the ID of the type of messages that we want to handle the requests for. So, next, of course, we need to add in a few handlers for our system state messages and perform the actual request. So we call request system state. We need to give that the connection to put these requests on. Sorry, it's not called connection. Then, of course, we need the name of the system state. And that's aircraft loaded. And then whatever handler we want for the moment the reply comes in. We'll put that on the next line. Use a lambda. And for aircraft loaded, we expect a string. And we'll just print that out. And that is all you need now to request the system state for aircraft loaded, and then as soon as it comes in, handle it. So let's copy this. 2, 3, 4, 5, 6. 6 times. Let's start with the second one, which is flight loaded. We'll rename this to flight. And the last one is flight plan. And let's not forget to remove that. No, that's too much. Just this one. Okay. Great. Then we have dialog mode. Now, dialog mode, we already said we expect that to be a Boolean. And I've given the request handler 2 versions for SystemState because actually this list that we're requesting here is the complete list of all available system states. So there are only strings or Booleans. We'll make that a bit simpler and just say if we get a true value returned, then the simulator is in a dialog, and otherwise the user is flying. Really simple. Let's be a little bit nice and just do it like this. Next one is the simulator state. And just like that one, we're going to say oh no. Okay, and then our unknown one. Okay. And this is all that we need to do. We don't need to add anything to the handling because we've already told the request handler to do that for us. The request handler will generate a request ID and then put this lambda as the handler for that particular request. So, I mean, we can add something like we expect the request handler, which is defined here inside the if. So after the if has ended, we can expect there to be no handler registered for SystemState because it needs to clean up. So let's just do that as a bit of a test, a sanity test. And we want the handler for the SystemState. And actually a function pointer or a function object in C++ is convertible to a Boolean, in which case it checks whether or not there currently is a valid function set. So if this is true, then the handler for SystemState was not cleaned up. Okay. And actually, this is all we need to do. So let's start the simulator and test. Okay. And let's run. And here you see that we get our answers just like with the C program. And we get one message of type 1, which is for the unknown state called SimLoaded. So this works. I'll just then for this time close down the simulator so we can check whether or not the cleanup was correctly done. And you see no complaints. It was cleanly removed. Now here I want to add a bit about a style of programming, or an architectural type as it's sometimes called, reactive programming. Working with callbacks opens up the path for this. With reactive programming, what you actually do is, instead of passing a callback, you actually get an object back that you can use and then ask for the result. This will block your current thread until that message comes in and it's available. This means, of course, that you're writing your program multi-threaded, and you write your program as if you immediately get the result. So instead of asking the request handler for the system state and giving it a lambda or a function to process the state as soon as it comes in, we're actually going to do a request handler request system state and then not give it a lambda, but instead on the result do, for example, something like a get. This works even better if we have a stream of results. But first we have to look at exception messages, because you saw in our program that we were requesting a system state that was not known. Exception messages can come at any time, and they almost always complain about something we did wrong. The message contains a reference to which of our messages caused it, and which of the parameters in that SimConnect call was the cause, if, of course, they can pinpoint it. So we have two fields there, a send ID and a parameter index, and there are defined values for the we don't know version of this. So there is an unknown send ID and an unknown index. So what is this send ID? The SimConnect library adds a sequence number to each message it sends to the simulator. You can ask it to give you the last one used, and this is what that send ID is. The call is SimConnect_getLastSendPacketID, and of course you have to give it the SimConnect handle and then a pointer to a unsigned integer for the send ID that it's going to put in there. The documentation states that this function is primarily intended to be used while debugging and testing the client application rather than in a final retail build. Well, I'm afraid I don't agree with that. This approach is like having a brand new ship and going out on sea trials, and then when you say, okay, the ship is fine, you remove all the lifeboats and life jackets because it was tested. It's okay. Yeah, I told you. I'm strict about error handling. So let's take a look at those exceptions. Our last example program caused a type 1 message, and it was ignored because we didn't have a handler for it. So let's fix that. We'll just do it in C++. Okay, we're now going to add the handling of the exception message. So we first need to add a handler method for that. And I hope you don't mind if I just copy that from another location, because it's pretty big, this list. What happens here is that we first get the exception value and cast that to the enumeration, so we can compare it with the enumeration values, and we type out the actual number. Then we check if we have a valid sent ID. There is a special value called unknown sent ID, which is not given in the documentation, but that is the value 0. So if we don't have a value 0 here, we know which message this was related to. And the same is for the index of the parameter. Now, in the documentation, it says that unknown index has value 0, but actually it has value maxint. So the safe way to do it is not to use the number, but just use the identifier for it. So if we have an index, then we print that. After that, we've got this very big switch statement with all the different errors. You will see a few legacy errors that are no longer supported by Flight Simulator 2020 and 2024, but were supported in previous versions of Flight Simulator. And at the end, you see a number of exceptions that are not yet supported, but are supported if you enable the experimental features. So now all we need to do is add another register handler call. For the SimConnect receive exception message. On this ID and handle exception. Okay. And now we can run, and hopefully we don't get an ignore on message 1, but instead get a exception message. So let's run the test. And here you see, again, the aircraft file, flight plan, user is flying, simulator is running. This is the dialog mode, of course. That's always on this side. And then received an exception type 7, related to a message with sent ID 7 regarding parameter 2. Parameter 2 is indeed the name of the system state. The parameter is not a recognized name. So here you see how useful these exception messages can be. Okay, now we've got most of the pieces ready to go from a single reply to a stream of replies. So instead of a system state, let's request events for the system state. This means that we're now going to get notifications of a change in that state. However, even though we start out with more or less the same program, we now get a different type of message back. SimConnect has an entire hierarchy of different events. There are events that contain file names, there are events that contain frame rate values, there are multiplayer events and AI events and even racing events. They all have different messages, different message IDs, and different message structures. There's even an extended event with more than one numeric value, and your program can determine what it is. The basic event just gives you an event ID, a group ID, and some value. The extensions provide the extra data. Now, that group ID is something we can use to put multiple event IDs into a group and then have a single handler that we can call when we get an event from that group. It can also be used to do prioritizing of events. We're not going to go in that in this part, but we'll get into that later. The event IDs, again, just like the request IDs, we have to make ourselves. So let's see how that works. Okay, let's rebuild this application so it is going to work with SystemState events. This is a bit different from what we have at the moment because we're now requesting system states, and with system state events, we're not going to use request IDs, but rather event IDs. They work in the same way, so let's just rename this to event ID. Copy that here and here. And of course, it's now not request system state, but instead we're going to use subscribe to system event. The rest of the call is the same. It needs the SimConnect handle, it needs the event ID, as I said, and it needs the name of the event. And we'll update the message. Like this. Also update the error message. Okay, this means, of course, that our request IDs now must become event IDs, and we'll make this a D word because that's what the parameter needs to be, and we'll change this. Let's keep this one and add the event sim started and event sim stopped. These are pretty simple events. The first one, SimState, just like before, it returns an integer, and that integer indicates whether the simulator is now running or stopped. And the SimStart and SimStop events, respectively, are just the SimState with value 1 and SimState with value 0, but then as a single event without any numerical data. Okay, let's go down. We need, of course, to adjust our handler. No need to change the open or quit handling, but now instead of a system state message, we're going to get an event message. Okay, then here we need to change this to match that. Cast here to that. Now we're not looking at particular request IDs, but we're looking at event IDs. And those are here. It's an unsigned ID. And let's just get rid of a few. We can reuse this one. Event SimState, simulator state, and this one also has now a different name. It's now the field DW data. Okay, and let's then add the SimStart and SimStop events. Just a simple message. Like that. Okay. We can leave the rest as it is. The only thing now, of course, is we need to update these. Let's start with SimState. And this needs to be event SimState. The string name is the same. The sim started event, and there the name is SimStart. So that means here we're looking for SimStop. Okay. Well, this is it. It's not longer, it's not request system state. Let's just do this nice subscribe to system event like this. See if we missed anything. Don't think so. No, this is fine. So let's see what happens if we run. Okay. Program started. We have subscribed to the system states. So SimStart, SimStop. And we already got one sim event saying that the simulator is currently running. Okay, let's fiddle a bit with this and go to the main menu, select free flight. I'm sorry you cannot see this, but let me just quickly here start a flight. You see, we get some extra events. You see that, by the way, SimStop or SimStart comes together with the sim event, which is not surprising because they have the same meaning. A sim event with value 0 is the same as a SimStop event, and a sim event with value 1 is the same as a SimStart event. Okay, And we'll go back to the main menu. Okay, that worked. Okay, now we go to the C++ version. And here we have to start with a bit of housekeeping on the events themselves. As you saw, events have a number, that's an ID, and we have to assign that ID. But they also have a name. Actually, when we request the event to be sent to us, we request it by name. So we're going to keep track of that. We're going to build two collections, two maps. One of them will map any event ID onto its name, and the other one goes the other way around and map the names to the IDs. This will prevent us handing out multiple IDs for the same event name, and it also makes it possible when we get a message for a certain event to get back the name for that particular ID. Now we don't have to hard code it in our code or use switch statements. This makes an event object just a number. Very fast, very compact. Since there is no request ID involved, we'll add, just like the request handler, an event handler. For now, we're going to assume all events are simple events. Let's see how that works. So we start from our request handler version of the program. We'll just remove this bit and start by making sure that we have the correct include files. As said, we're not going to look at this as requests, but rather events. So we now have an event handler. Apart from that, we also make use of a convenience include file, which gives us the system events. This is because we want the event object rather than just the name or just the ID. Okay, we'll start here now, and we can start by creating an event handler. Give it the obvious name. And then enable it on this connection. Which we do through the top-level handler. Now for the event handler, we don't need to pass it the IDs of the messages. For requests, that is necessary because you can have requests associated with different types of requests. Here we're always talking about events, so the event handler knows the types of messages. And the current version in the header file only picks up the base events, which are events with a single numeric value in them. So then the next thing, of course, is to subscribe to those events. Subscribe to system event. And we'll give it the connection, just like before. And now we need to give it the event object. So here we're going to use those system events. And you see that those system events are available because we included that file, and we'll start by the sim. It is a call, and that's just an inline call that creates the event object. And all we need now is the lambda for handling this. Now, difference here is the handler does not know, or the event handler does not know that we want a Boolean, so we just get the object or the message. And we'll just print out the typical messages. We get the data from the event, and if that is unequal to 0, we can then say that the simulator is running. And otherwise it's stopped. Okay, that's the first one, and we'll also take, just like in the C example, SimStart and SimStop. For SimStart, the actual contents of the message don't care. If we get this message, we know the simulator has started running. And of course, that means we're not doing anything with the actual message. The SimStop message, similar approach. Like that. Okay. Now, because we are using events and we're building those events as just the IDs with their names, we now have a few static fields that we need to take along. They are in source files rather than in header files. So we need to add those to our solution. And I'll do it just like this. Go into the directory here, the source directory. There is the CPP SimConnect project file. I can add that, and then I need to add it as a reference. And of course, we want also to update the project dependencies. And verify that that is selected. Okay. Build is now successful. So let's run it. And you see it works. We got our simulator or a sim event, just like before. And on the other screen, let me just do some things with the free flight, and you will see some messages come in. And you see that every time you have a sim event, you also get the corresponding sim start or sim stopped event. The simulator has stopped is the sim stopped event, sim stop event, and simulator is stopped is the sim event after that. And here the simulator has started running, that's the sim start event, and then again a sim event, and now with value 1. Okay, this was a really big part, but I think this is a good point to stop part 3. So today we looked at the messages flowing from the simulator to our app. We looked at the different ways we can detect if a message has arrived, and we used that to detect and obtain the message telling us what simulator we are communicating with, as well as the one about the simulator shutdown. Then we asked the simulator about its state, and first as a one-off request, and then later in the form of events, and we looked at how to deal with those messages. We used C++ classes to build a library that can help us to manage this and manage our callbacks. Now, about all those C++ classes that we've built and we're using. While looking at the examples of our library, you may have wondered about the frequent use of methods, sometimes even for the simplest of actions. And sure, they make our code a lot more readable, but isn't there a cost involved with all those calls? Isn't it cheaper and even faster just to directly interact with the associated fields or variables like we would do with a C program? And here the answer is actually no, not necessarily. This is something that is taken care of in the C++ standard. The C++ compiler will consider any method in a header file as an inline method. That means that it is allowed to just put the contents of that method at the spot where we call the method. So a getter method, which does nothing but return the value of a private field, does in that case exactly the same as directly accessing that field. For a release build rather than a debug build, the compiler will do those optimizations, and it will do a lot of those optimizations. You might, if you look at examples of how that works, find out that even things like passing a string object is actually nothing more than passing the string as a C string directly into the code that's going to use it, and it will get you amazing optimizations. The compiler really is your friend, and you shouldn't be afraid to use these things. So how are we going to continue? Well, next time we're going to go for the more complex messages. We're going to look at complex blocks of data. To do that, you first have to tell the simulator what kind of data you want to put in such a block, and that's called the definition block. We'll discuss how you can do that. We'll build blocks of related data items and then ask the simulator to send it to us. We can ask it to send it every second or maybe even every frame. We can tell it, don't bother if there is no change, or if it's a floating point value, we can say, I want the change only if it's at least this large. This is an important subject due to all the different requests that use them. Obviously, you can use this for information on the user's aircraft, but you can also use it for all the AI aircraft that are available. You can use it for the ground vehicles, and you can also use it for requests about airports and airports facilities. So again, let me finish this up with all the sources are on GitHub. Please go there, check it out, and take a look. If you have a suggestion, either for a change in the code or a lesson or a subject, please create an issue. And remember, I'm mostly in this for the subs and likes, so if you like it, please leave one of those. You're also free to leave comments, but I can't promise prompt replies on those because I also have a normal daytime job and a family. So thank you for your time and see you in the next one.